Hi and welcome to Quick Solutions All India AIATS Test Series JEE Advanced 2020 Test 3A Paper 1 Code C and D Physics. Let's go to question number 1. Question 1 says, in the circuit shown, the switch S is closed at t equal to 0. If R is equal to under root L by 2C, then option A says initial current through battery is E by R. Option B says steady state current through battery is E by 2R. Option C says current through resistor R and 2R are equal at T equal to RC ln 3. And option D says current through resistor R and 2R are equal at T equal to 2RC by 3 ln 3. Okay, well, we can see that the question is clearly from the topic current electricity. In fact, it also involves transient currents in LR circuits and in RC circuits. Right? So, well, there is an inductor, so there is concept of EMI also involved in a way, and of course there is a capacitor. Now coming to current at t equal to 0 just after closing of switch. So at t equal to 0, if I say the current in the capacitor is IC is equal to E by R. Now the reason is that the capacitor is initially uncharged and it's simply going to behave like a connecting wire. Initially at that instant, right, when it is totally uncharged. So at that time, this is the current IC, and current through the inductor at that instant will be 0, because the inductor we know is going to offer infinite resistance at that instant, and current through that branch is going to be 0. So that means that current through the battery, capital I, which is simply IC plus IL at any instant, is equal to E by R, and which means that option A is correct. Let's look at option B, which says steady state current through battery. Well, in steady state, and the steady state is going to be achieved at t equal to infinity. So at that instant, at t equal to infinity, we can see that the current through the capacitor is going to be 0. The capacitor is going to be fully charged, and current through that branch is 0. So that means IC is 0, whereas IL will be simply E by 2R, because the inductor in steady state is simply going to behave like a connecting wire of 0 resistance. So this means that current through battery capital I is also E by 2R, which means that option B is also correct. Now to evaluate options C and D, we need to look at expressions for the transient current as a function of time. So current IC at time t is the initial current through the capacitor, that means E by R into e to the power minus t by the time constant, and the time constant is RC. This is the current in the branch having capacitor. Similarly, current in the branch having inductor is the steady state current, which is E by 2R into 1 minus e to the power minus t by time constant for this circuit, which is L by 2R. Now to find the time at which IC and IL are equal, we put IC equals IL and also use the fact that R is equal to under root L by 2C. We simplify and solve. We find when we apply this condition that T comes out to be equal to RC ln 3, which means option C is also correct, whereas option D is incorrect. So that means for question 1, options A, B and C are correct. Let's now go to the next question. Question 2 says, which of the following equations is R-dimensionally correct? Now capital E stands for electric field, I stands for current, L stands for inductance, small l stands for length, R stands for resistance, and C stands for capacitance. Well, we need to evaluate each and every statement. Well, let's evaluate option A, and dimensions of I square by L very clearly is A2 L minus 1. Very simple, straightforward. Whereas dimensions of C by E, to find dimensions of C by E, C is Q by V. So dimensions of C by E can be written as dimensions of Q divided by V, and V itself is dimensionally E into length, so that means it is E square L. Now this is again Q divided by E is F square by Q square into L, and then its dimensions will be then A3 T3 divided by F square will have dimensions M L T minus 2 whole square and of course there is length here. Well, without doing further simplification, we can clearly see that the right hand side has dimensions of m minus 2 and the left hand side does not have any dimensions of m. So option A is incorrect for sure. Let's look at option B now. In option B we have epsilon naught E square by I square on the left hand side and capital L by LQ on the right hand side. Well, so we can rewrite equation given in B as epsilon naught E square is equal to, dimensionally, the statement we have to evaluate of course is capital L I square by LQ, dimensions of this quantity. Now this has dimension of energy density, right? We know that energy density in electric field E in vacuum is half epsilon naught E square. So this clearly has dimensions of energy per unit volume. We also know that Li square has dimensions of energy because half Li square is the energy stored in an inductor, and of course dimensions of volume in the denominator. So both the left hand side as well as the right hand side have dimensions of energy per unit volume. So option B is clearly correct. Let's look at option C now. Well, the equation we can rewrite as L by R, dimensions of L by R is equal to dimensions of 2RC or 2CR. Well, both sides have dimensions of time. In fact, they are L by R is nothing but time constant in an LR circuit, DC LR circuit in fact. So, and this is the time constant for an RC circuit. So both sides have dimensions of time. So the equation is dimensionally correct. So that means C is also a correct option. Let's look at option D. Let's write the equation given in D as L by R is equal to 1 upon ILC. We can rearrange this equation like this because L by R will be equal to then 1 upon ILC. Well, the left hand side has dimensions of time. Dimensions of L by R we discussed in the previous option also is simply T. Whereas this quantity will have dimensions of, that means dimensions of 1 upon ILC. We know that omega square is 1 by LC in LC oscillation. So this quantity 1 by LC has dimensions of T minus 2 and I of course has dimensions of A. So we can see that dimensionally this is not correct. Equation D is not correct. So that means for question 2 only options B and C are correct and the other two options are incorrect. Let's now go to the next question. Question 3 says 3 identical lenses each of focal length f are arranged as shown in figure. A small object is placed at distance f by 2 as shown. Then, and this is the figure given, 3 lenses have been arranged and object is at distance f by 2 from the first lens, and option A says the final image is real. Option B says the final image is inverted. Option C says the final image is of same size as that of object, and option D says final image is virtual. Okay, so let's apply the lens equation for refraction by the first lens. For the first lens we can see that the value of u, the object distance, can be taken as minus f by 2, and let's apply the lens formula. So the image position, let's call it v1. 1 by v1 can be written as 1 by f plus 1 by u. So plus 1 by u, which we can rewrite as 1 by f minus 2 by f, and this is coming out to be equal to minus 1 by f. So v1 is minus f, right? So the first lens is forming an erect image, in fact erect as well as virtual and enlarged image, right, of the object. So that is about the first lens. Now for the second lens, then the value of u will become, the object distance will become f plus f, right? Because the image by the first lens is to the left of the first lens at distance f, somewhere here, okay, somewhere here, and this distance is f, so this distance becomes 2f. So the second lens will form now an inverted real image, and the size of image will be same as the size of the object, which is already magnified by the first lens, right? And the second lens is going to form image on this side. In fact, it's something like this. Second image is going to form image on this side. Now 2f distance from the second lens, that means from the middle lens, somewhere like this. So now we need to look at refraction by the third lens, right? So for the third lens, the value of u will become, since this distance is 2f, this distance is f, so u is now plus f, right? So as far as the third lens is concerned, for it the object is a virtual object and u is plus f, and so 1 by v is 1 by f plus 1 by f, that means 2 by f, and the value of v is f by 2. So that means the magnification produced by the third lens, we can call it M3, is v by u, that means 1 by 2. And if we work out the total magnification, well, in fact M1 was 2 because both the image and the object were on the same side of the lens. Both u and v were negative, so M1 was 2. M2 is minus 1 and M3 is 1 by 2. So if I take total magnification M1, M2 and M3, the product comes out to be equal to, M2 was minus 1, so this product is coming out to be minus 1. Okay, so which means that the final image is real. Clearly there will be actual intersection of rays at distance f by 2 from the lens on the extreme right, and the final image will also be inverted with respect to the object. The final image will have same size as that of the object because the total magnification M1 into M2, M2, M3 is turning out to be minus 1, and option D will be incorrect. So that means for question 3, options A, B and C are the correct options. Let's go to the next question now. Question 4 says, in the arrangement shown, the rails are smooth and of negligible resistance. The rod is of mass m and length L, negligible resistance, and it is projected with velocity v0 as shown. Transverse uniform magnetic field B is present. Then the options are: the rod acquired terminal velocity, the rod performs SHM, maximum current in the loop is this much, and minimum current in the loop is 0. Well, the question obviously involves concepts of electromagnetic induction, and also since there will be current and there will be a magnetic force too. So the magnetic force on a current carrying conductor, electromagnetic induction, these are the concepts involved here. Now we can see here, well, if the rod is moving towards right, let's say with some velocity v, then we can see that the flux through this loop is increasing in magnitude and magnetic field is in the upward direction. So that means, as per Lenge's law, the induced current in the loop will be in the clockwise sense, right? So this is how the current will flow when velocity is towards right, and this is the way the current is going to flow. This is how it's going to flow. Now let's apply the Kirchoff's law for this loop. So we have BLV minus L di by dt equal to 0 as per Kirchoff's law, in fact Kirchoff's loop law. Let's try and simplify this still further. So we have, if I write V, in fact we write V as dx by dt. So if I take displacement from initial position of the rod as x, let's say the rod has come here, then BL dx by dt, we can say is V, is equal to L di by dt. Now at time t equal to 0, right, that means just after projection, the current in the loop is going to be 0 because the inductor will not allow any current to flow, right? And which means that we have BLX by integrating initially at time t equal to 0, x is 0 as well as I is 0. So that gives us BLX is equal to Li, right? So this is the expression we have. And as far as acceleration of the rod is concerned, acceleration of the rod is the magnetic force. We can see that by applying I into L cross B, the magnetic force is towards left. And so A will be negative. It's minus. The magnetic force is BIL. That means it is BIL and divided by mass of the particle. So this means we have dV by dt is equal to minus BIL by M, and which is again minus B small l divided by M, and the capital I can be written as B small l by capital L into X. So we have an equation, a differential equation, which is same as a differential equation for an SHM. That means we have essentially d2x by dt square is equal to minus b square l square by m into l into x, so which is what we call as the defining differential equation for SHM. So it means that the rod will perform simple harmonic motion, SHM, and so option A is incorrect and option B is correct. Now to find maximum current in the loop, we can in fact conserve the total energy, and when current in the loop is maximum, we can assume that the kinetic energy of the rod is 0. So the total energy of total of the kinetic energy of the rod and the magnetic energy stored in the inductor is going to be constant, and its value will be half mv0 square. So we have half mv0 square is equal to half capital L I max square. Now if I solve, the I max value comes out to be equal to V0 under root m by capital L. So that means option C is correct, and minimum current in the loop will be 0 because the rod is performing SHM, and we can see that x is proportional to I. So when x is 0, I will also be 0, and that is the minimum current in the loop. So minimum current in the loop is 0 is also a correct option. So question 4, options B, C and D are correct. Let's now go on to the next question. Question 5 says a long hollow cylinder of radius r carries current I along its length. Current is uniformly distributed along its circumference. Then magnetic field on axis of cylinder is 0. Magnetic field on axis of cylinder is mu naught I by 2r. Magnetic pressure on the surface of cylinder is this much, and magnetic pressure on the surface of cylinder is this much. Okay, so to find the magnetic field, well, we can apply the Ampere circular law, right? And if I take this as the cross section of the long hollow cylinder, okay, so the current is, let's say, coming outward and the total current is I. Now to find field on the axis, if I just take an Amperian loop like this, okay, and do a circulation of B, the current enclosed within this Amperian loop is 0. So the magnetic field is 0 in fact everywhere inside the shell. So that means the magnetic field is 0 even at the axis of the cylinder. So that means option A is correct and option B is incorrect. Now let's look at the magnetic pressure on the surface of this cylinder. Well, we just saw that magnetic field inside is 0, and if I work out magnetic field just outside of this, then the same and apply again Ampere circular law for this loop. We can take the radius of loop as r only. We are talking about just outside the cylinder. So B into, see, the Ampere circuitous law says integral, closed integral of B dot dl, and this is a line integral, is equal to mu naught times current enclosed. So B times B dot dl will give us B into 2 pi r, and the current enclosed will be the total current, so it's equal to mu naught I on the right hand side. The value of B is mu naught I divided by 2 pi r. This is the magnetic field just outside the cylinder. Just inside the cylinder, the magnetic field is 0. So that means if I just consider a small portion, let's call this length as dl, a very small length dl from its cross section, and let's say along the length, right, the other dimension of this strip will be, say, capital L. So we can see that if I consider contribution of this part to magnetic field, we can see that on this side and this side, magnetic field due to this part is in fact in opposite directions. So the magnetic field due to the rest part and magnetic field due to the strip, small element that we have considered, they are cancelling each other on the inside of the shell, and whereas they add up on the outside of shell. Now sum of the two is coming out to be this. So that means we can consider that magnetic field due to the remaining part of the cylinder, excluding the element that we have considered, we can call it B dash. B dash will be B by 2, half of total magnetic field. Again, I am repeating the argument. The argument is this, that vector sum of two magnetic fields just inside is 0. That means their magnitudes are equal, and just outside it is this much. So magnetic field due to one part, and in this case that one part is the remainder of the cylinder, will be B by 2, and which is nothing but mu naught I by 4 pi r. So this is the magnetic field, and this is the external magnetic field, and due to this magnetic field we can work out the force acting on the element. So the force acting on this element will be this magnetic field, which is mu naught I by 4 pi r. Remember, the magnetic force we say is I into L cross B, and here the field and the L vector are mutually perpendicular. So suppose we consider length L of the strip, then the force on that length L of the strip will be equal to this magnetic field into whatever is the current in that strip. Now the current in that strip will be I dl by 2 pi r by unitary method, right? And the length we are considering, let's say, capital L. So this is the force, and if I consider force per unit area, that means F by L dl, then this is the pressure which is experienced by the surface of the cylinder, and that expression will then be equal to mu naught I square divided by 8 pi square r square. Now if I look at the expressions in C and D, well, this is matching with option C. So option C is correct, and option D we can take that it's incorrect. So for question 5, options A and C are correct. Let's go on to the next question now.